So, we're doing videos on Bernoulli's, which is flying, and on gases, and I asked my wife what I should get, and she said a great gas mask would be a great kind of hat to make. And she said they might have my costume shops, and she said she would go and look, and this is what I got back instead. No gas masks. A little tiny witch's hat. That's what I'm going to live with for this one, which is on kinetic theory, which has a lot to do with gases. So this section has a lot to do with gases, and then how that leads into heat, and how that leads into heat engines. We don't actually get to heat engines until next time, but it's sort of leading that direction. We start with kinetic theory. What kinetic theory does is it takes what we know about Newtonian mechanics and energies and collisions and all that stuff, and it applies them to individual gas molecules. So it has little things that are flying around in a gas, and they're flying in all different directions. And they make like 2 or 3 little assumptions, and when they do that, all of a sudden the heat energy thing makes a lot more sense. And these assumptions are definitely on the test as concept questions for like what this is based on. And the first one is that there are a lot of really small molecules. So the distance between the molecules is big, and they only collide every now and then. They're going in all different directions at different kinds of speeds, but there's an average speed, which we call the root mean square speed, that we're going to use for some of our equations later on. It says that mostly they don't interact. That's that second one right there, since they're so far apart. When they do collide, we're going to say that they only follow Newton's laws. In other words, they're going to hit, do our little collisions. We're going to say that they're always exactly elastic, which is what this says. But we're going to say that the electric forces and the magnetic forces and all those things are not as important as the actual collisions and energies and forces that are involved in just them moving. And if we start with these 4 rules, we end up with these two. These 2 equations are the energy, the molecular energy, kinetic energy, that moving around randomly in big amounts. This one equation right here is for the whole sample of gas, and so that has the number of moles, that little n in there, and so that's the energy of the whole thing. This one here is the energy of one molecule, and notice it's got a new constant. Its Boltzmann's constant is the same thing as R over Avogadro's number, so if you remember your chemistry, that's related there. And you can get them to each other by multiplying by the number of molecules, because the number of molecules has to do with Avogadro's number in some weird chemistry way that I don't get. In reality, we don't really use these 2 equations so much putting numbers in. Maybe once or twice, mostly in Quest, not really on the test. For us, in physics, what we learn from these 2 equations is that the average kinetic energy is proportional to temperature. So in other words, temperature is the same thing as the motion of gas molecules through the air. So from these equations, from kinetic theory, we learn that heat is the same thing as molecules' kinetic energy. If we set those kinetic energy formulas we had on the last page equal to 1/2 mv squared, we can get the average velocity of each individual molecule. And again, don't use them very often in a problem, maybe once or twice. There are 2 different ones. One uses the molar mass, that's the upper one, and one uses the mass of one molecule. And so they have different constants in there, with that Avogadro's number thing worked in there. So basically we just set k equals delta U, we solve for our v's, and really it's just about that same proportionality, is that the temperature is proportional to the velocity. In this case, it's the square root is involved because of 1/2 mv squared. But just like the last one, not so much problems, but ideas. When we're dealing with work for particles, we use the formula work equals force times distance, and so we get a force distance graph, and we have to find the area underneath that curve to find the work. But when we're dealing with fluids, we don't really have a set distance for a fluid because it's kind of moving around, and the force on it kind of mushes in, it doesn't make the thing move, and so it works a little different. But we know that pressure is our force of liquids, and so we take our pressure equals force over area, solve it for force is pressure times area, and we plug it in for force, so we get pressure area times delta D equals work. And then we combine our area times distance. That's length and width is area times height, which is distance, and we get volume. So it turns out that the work for a gas is the pressure it's at times the change in volume. And so this equation here is what we're going to use for the work of a fluid, both liquids and gases, but mostly gases really for this one. And if you notice, it's got a negative in it. And that negative is, shall we say, controversial in physics. Every physics book that we have, including ours, actually says that work equals P delta V. The AP test wants it to be positive for work done on the gas because of the other work we did. This same work up here, they want everything to be the same. And so they put a negative in there, which makes all of our calculations a little weird. So if we have a pressure volume graph and we want to find the work, we would normally just find the area of this little triangle right here, right? We would take the pressure, which is 2, times the change in volume, which is 4 minus 1, which is 3, we get 6. And that'd be the work done by the gas. But since AP wants a negative in there, we actually get a negative 6 joules for the work done. So anytime we have something moving to the right along that, from 1 to 4 in other words, we get a negative number. And so for us to get a positive number, this negative has to be canceled out by an arrow going back to the left, which would make this negative plus a negative in the equation would make it a positive. That's a little confusing. I'm anticipating some questions on this, and we will go over it. We're continuing on in the theme of snacks that I steal from my son. He's not looking right now, he'll never notice. The next one is queso. Now, I have had a bit of queso in my day, but I do not order queso myself anymore, really, ever. It's not that good for you, I know, and I'm watching cholesterol. I hate that I am, but I am. But if my son orders it, do I sometimes occasionally encourage him to order it? I do sometimes. When he orders it, or when we make it at home, I have a ton of it. And I realize that most of you probably already know how to make queso, but in case you don't, this is something that everyone needs to know. You need to have Velveeta, and you need to have a can that has jalapenos and onions and tomatoes. Rotel's the best brand, but they didn't have it, so Rotel should be what it says there, but doesn't. Little can of that. You take your Velveeta and you dice it into something that looks just like this. You open your can. Oh gosh, that took a long time. And then you take it, you dump it on. You throw it in the microwave for 2 minutes, and you end up with perfect queso. And it is so amazing. Okay, so now we know a little bit about work with gases. We know a little bit about delta U being change in temperature, basically. And we have to add one more thing to get to engines. And that's the first law of thermodynamics. The first law of thermodynamics says that if we have a piston, which is what this is basically down here, the most simplified kind of engine, just one piston. If we explode a gas in there, this goes outwards, makes the wheels move over here on this side. It all starts with Q. Q is the heat transferred to the system. And so that's basically, I explode some gasoline in my engine. I want most of the energy of that to make the piston go out, to make the wheels go around, essentially. And if I do that, I get some force and some distance, and some work is done on the world. Remember that that's negative work done on the system, and weird AP people, thank you for doing that, but it's a negative one. So it's going to do some work. Anything left over makes the gases that are inside this little piston move around faster and have a delta U. So essentially, when we have a gas that's inside of there, its change in energy, delta U, is going to be whatever I put in minus whatever work is done by it. Now remember, the negative goes away, so it's a minus a negative work, and so it becomes a plus a positive. So that's why our version of this is delta U equals Q plus W, even though everyone else's is delta U equals Q minus W, because it makes more sense in an engine to say W is positive when it goes out. Don't dwell too much on that. I'm not going to. I'm going to have a little bit of queso instead. Yes, queso for me. These are all energies in joules. Some goes in, part of it goes to change the temperature, part of it goes into doing work on the world, which is negative work done on the system. All right, we're working our way toward heat engines, and we have to use some vocabulary to do that. And we're going to define certain kinds of processes. Processes are things that happen that change either U or Q or W. Because W is related in there, we have to use the equation W equals negative P delta V. And since P and V are in there, a lot of times we use P of net. So those are our three main equations we deal with processes. We're going to do some definitions. The first one is a cyclic process. A cyclic process is something that goes around in a circle, ends up back where it starts. And we like to show that on a PV graph. All of them will have a PV graph for them. And a cyclic process would go from A to B to C to D and back up to A. A, B, C, D, A is a cyclic one because it goes all the way around this little circle back to where it starts from. If it goes back to where it starts from, then P and V are going to be back to where they started from. And since temperature is proportional to P and V, since N and R are constants, it goes back to the same temperature. If it goes back to the same temperature, it goes back to the same delta U, since delta U is proportional to temperature. So in a cyclic process, delta U is 0. If that's the case, when you plug delta equals 0 up here, Q equals minus W. So in other words, if we have a cyclic process, all the heat that's entered into the piston does work on the world. That's the negative W because it's negative work done on the world. Okay? We can't ever really get this in real life because we don't get 100% efficient engines. We'll talk about that next time. But if we did have a cyclic process that went exactly where it started, delta U be 0, Q be equal minus W. Yeah, that's it. Next come the two easy processes. Our next process is called isobaric. Iso meaning same, and baric meaning pressure means it's a constant pressure. And that means that on our PV graph, it has to go at the same pressure value. So either it goes that way or that way, like A or like B. And for isobaric processes, all of our formulas hold true. We can find out that since my P stays constant, if my volume goes up, my temperature goes up. If my volume goes down, my temperature goes down. If, for instance, I'm going to the right, I know that my P delta V is going to give me a negative number, so my work is going to be negative. But I know that my temperature goes up, so if this goes up, this is going to be positive. This one's going to be negative, so my Q has to be very positive. That's a little much. We'll get to that stuff a little later. But essentially, all of my equations hold true, and I can find everything that I need. And realize that my delta U equals Q plus W, I can change that down here. Delta U is 3/2 kBT. Work is negative P delta V. And so there are occasionally times where I'm going to set all those into my first law of thermodynamics. And isobaric ones are generally the ones that I would do that for. Isovolumetric means same volume. Iso, same volume. And so on a PV graph for that, since I have the same volume, I'm going to go straight up or straight down, this way or that way. And since I have delta V equals 0, my work is going to be 0. That's why my piston doesn't move. And that means my delta U is Q. And so that means that any internal energy, any energy that I add into my piston is going to change the temperature. Q goes into W in an isovolumetric. An old name for that is isochoric. But that's isothermal, same temperature. Have the same temperature, then because delta U is 3/2 kBT, my delta U ends up being 0. If my delta U ends up being 0, then Q equals minus W, which means any energy put into the system changes the volume or makes the piston expand, does some work on the world, negative work done on the system. Now, since PV equals nRT, if temperature is constant, PV equals a constant, Then if I did a PV graph, it's P equals constant times 1 over V. That's a 1 over V graph. And so I get that shape that we are familiar with. And so it looks kind of like that curvy shape. And notice that if we have two different isotherms, a high temperature and a low temperature, high temperature will always be farther up and to the right because we know that since PV is proportional to temperature, my pressure, my volume would be greater to make a greater temperature when I get the isotherm up there. And so this will be at one temperature, this will be at another temperature, that will be higher than that one will be. And so it's a little more complicated because it's not a straight line like our first two, it's a curvy one, but since we have this nice relationship that comes from Pvnert, which is our friend, it's friendly and it's all good. And then there's adiabatic. Adiabatic's the weird one. Adiabatic, by definition, no thermal energy is transferred. Ooh, that's another thing. No thermal energy is transferred means that Q equals 0. So an adiabatic Q has to equal 0. Now it turns out that adiabatic has a very similar picture to isothermal. It's also 1 over x function, but it has a plus b. You know how we had a plus b and y equals mx plus b? And so it's not actually a 1 over x function. It, like if you take 2 points on it, they don't, like if you did it for an isotherm, if you took this one and that one and you multiplied this p times that v and this p times that v, you get the same number. And so you know it's an isotherm. For adiabatic, because that plus is in there, you can take 2 points and they won't be equal. And so that's how you can tell the difference between an adiabatic and an isotherm. I'll do an example for that in class, but essentially it is a 1 over x shape, but it's shifted up or down on the graph a little bit. So you can tell the difference between this kind of graph and the isotherm graph that we just talked about a second ago. If Q equals 0, then by the first law, we know that delta U equals work, which means that any change in temperature makes my piston expand or contract. So we ended on some weird process definitions that we're actually going to use next time. Make sure you understand what the processes are, and we'll talk about how we use them later. As we leave to the sound of my friend the witch doctor, my friend Pvnert, witches, just want to mention why this particular hat is so appropriate to me. It turns out that in my ancestry is a famous witch. Her name is Rebecca Nurse. This is her gravestone there. She was probably the most famous hanged witch in the Salem witch trials. I am related to her. And one of the reasons she was famous is because she was a great person and she was killed anyway. And so it sort of led to the downfall of all that, deciding people were witches because we didn't like them and killing them stuff. But anyway, I have witch ancestry. Maybe this hat is perfect for me. Go off. Do physics.